Okay, so let's have a look at the solution to the Week 3 DC homework for UEENEEE104A. This is set each week, of course, and I did guarantee to give you a solution to the homework. So I've actually had a colleague quickly do this solution for me today, and there's a couple of small things that he wasn't quite sure of that I will point out. Now, in this first circuit, it's pretty straightforward. It's got an ammeter. You can see that the negative on the power supply is connected to the negative side of the ammeter, and the most positive side of the power supply to the hot part of the circuit, and then this is more positive compared to the negative terminal, so it has to go to the positive side of the ammeter to get the deflection going in the correct direction. Very important not to get the ammeter polarity back to front. We had to trace out the circuit, and you can probably see here already that he's kind of traced that out, and that goes up through there, down through there, over to there. Bypasses are too. It's not even used in the circuit. And again, back into the meter there, and the meter back out to the power supply. So in so doing, we ended up with RT was 22k plus 10 plus 1k, 33k. The only thing here, see this question mark? Look, there was, I think he thought it was 1.685, but I did write over here high voltage. And I'll just take a moment to go and have a look at what that high voltage means. If we go into, if we go into here and we look at Safe Work Australia under Managing Risks, and you'll find this in many of their other documents, but this is a code of practice for manage electrical risks in the workplace. And we have high voltage. Here, high voltage means voltage that exceeds low voltage. Well, it doesn't mean much by itself, but if we then look at low voltage, we see that that is direct current less than 1500 volts DC. So in other words, high voltage means voltage that exceeds 1500 volts DC. I guess maybe they should have written it that way. Extra low voltage, we've talked about that also, means voltage that does not exceed 50 volts AC or 120 volts DC. So it's pretty weird when you think about it. You know, low voltage we call anything less than 1500 volts. I kind of wouldn't want to put my hand on something that was 600, 700, 800 volts and think, oh, that's okay, it's just low voltage. But nevertheless, that is the definition from Safe Work Australia. And today we've got this first problem talking about high voltage, which by definition here means voltage greater than 1500 volts DC. So let's go back to our question. We've got a solution then, and I'll just change that. I'll put a comma in there. We might just go for a smaller pen, and we'll put a comma in there then. So 1685 volts divided by 33k, and that won't be microamps because we've increased the magnitude of the voltage by 1000. That can come up to milliamps now, 51 milliamps. Continuing on to the next question. This is a very common barrel connector used in the electrical and electronics industry. And again, you can see here what my colleague has done. I'll just choose something a little bit light there. Through that first resistor, up through the barrel connector, through the second resistor, back down and comes out through another resistor, and then up through there and down there, and oh, isn't this fun? Up through there and down through the last resistor, and that actually is the input, and there is the output. And the question was determine the total resistance. That is 107 ohms, because there's 10, 22, 27, 15 and 33 ohm resistors. They are all written quite clearly on the paper. Of course, this is in black and white. You had the original handout given in colour. At least the PDF was in colour, and if you downloaded it in colour, you might have noticed that I think the colour bands on the resistors did not line up to what was written next to them. That's because I've kind of cheated here. I've used the same question before and I've just changed the values of the resistors, and it's too hard to physically put the exact values back in each time I reuse that question. So, you know, based on that, you could probably expect to see that question again maybe, but with some different values and the question used in a slightly different way. 107 ohms is RT then. That's good. Figure 2, if the 22 ohm resistor becomes short-circuited, well, any resistor with a short circuit across it becomes 0 ohms, so it's no longer in circuit. We simply had to get RT minus 22 ohms, and that gave us 85 ohms, which is correct. Another question based on that, in figure 2, if the 27 ohm resistor becomes open circuit means you've got the cutters and you've actually cut through it. So in other words, we've had a resistor, and use the European symbol there for the resistor, and somebody has come along and they have cut the wire perhaps. So the wire's been cut. It's now going to be like this in circuit, open circuit, and the resistor could have just burned out, but I mean, I'm using this example that it's been cut. So you've got this break in the circuit, and while you've got this break in the circuit, no current can flow. If no current can flow in the circuit, we're going to have an infinite amount of resistance measured across the whole thing. You know, you've got your digital multimeter, you put it on the ohms range, and you go to measure air. What do you get? Well, the meter doesn't change. It just shows OL, or out of range, or infinite resistance. That's all it's going to show. Got a new circuit now. Figure 2, you are to examine the layout. Oh, I see. Same circuit. Yes, same circuit, but we've got to examine the layout and sketch a new circuit schematic diagram. So that's 24 volt supply coming in 10, 22, 27, 15, 33, and then we've got all these wretched questions that we had to answer here. Very typical electrical exam type question. RT 107 ohms. IT 224 milliamps. V on the 10 ohm resistor, the voltage across the 10 ohm resistor. V equals I times R. And you can see all of these answers. I've confirmed that they are all correct. The powers, I've already confirmed that they were correct. And when I say I confirmed that they were correct, I cheated a little tiny bit here. Sometimes I do this, but more so today I just wanted to demonstrate that if you use something like iCircuit, and we've looked at this before, you can make the circuit up. Here's our 24 volt supply, 10, 22, 27, 15, 33 ohm resistors, and simply then by selecting one resistor, such as the 22 ohm resistor, I can see that it has 224.3 milliamps flowing through it. It's got a voltage dropped across it of 4.935 volts, resistance of 22 ohms. The power dissipated in that resistor is 1.107 watts. And the same if we go and we look at the 33 ohm resistor. This is the largest resistor in the circuit, and it's going to have the same current flowing through it, but therefore, because V equals I times R, it'll have the largest voltage drop across it. And VD there, 7.4 volts. If we go back to the 10 ohm resistor, that one being the smallest, that should have the smallest voltage drop across it, and that has 2.24 volts dropped across it. Again, they all have the 224.3 milliamps, and we can even see that if we go to a piece of wire there in the circuit, and just shrink that circuit down a little bit so that we can see that 224.3 milliamps traveling at all points in the circuit there. 224.3 milliamps you can see traveling at all points in that circuit. So going back to the actual exam notes, the powers all add up exactly. And P total down at the bottom. PT equals P10 plus P22 plus P27 plus P15 plus the P33. We learned that in class, and we can simply use P equals V times I for the entire circuit. And that will be the 24 volts times the 224 milliamps that we have flowing in the circuit. So we've run a check on that. It rounds up to 5.38 watts. If you were to add up all of the individual powers on each resistor, they will add to 5.38 watts as well. And big questions like that are always worth a lot of marks. That one's worth 12 marks, in fact. The next question. I love this layout. This is so classical, and it's something that I grew up with, especially with the valve radio era, and having these tag strips and different resistors distributed across the tag strip. Maybe it could be used for something like, what have I got on the side over here? Voltage divider. I'm going to do another small video on voltage dividers later, and this would be a very typical tag strip set up for a voltage divider, where we can take a different voltage from this point here and a different voltage from this point here. So that'd be our input voltage, Vs, and that'd be, where's our first port of call? That'd be V1, that'd be V2, and this is the probably ground at this point here, if it was a typical type voltage divider. At any rate, sketch the circuit diagram for that, and we had 48 volts, 68 ohm, 27, 39, RT, 134 ohms, tick, and the current flowing through it, we had 358 milliamps, and the total power is 17.18 watts because P equals V times I, so the 48 volts times the total current, which was here. The voltage on the 27 ohm resistor, V equals I times R, 0.358 times 27 times 39 times 68, and here are the voltages shown over here. So you can mark your own work against those. And of course, easy to check if they're correct because they have to add up to 48 volts. Kirchhoff's voltage law. The power on each resistor, P equals V times I if you like, or you could use P equals I squared times R, or P equals V squared on R. It's your own personal choice which one that you use. 3.44 watts, 5 watts, and 87 watts. And if you add all of those together as well, they'll add up to 17.18 watts, which is the total power. So that's a good quick check that you can do on something like that. Show the range of values in ohms the 68 ohm resistor can be. Well, it's a 5% resistor, and to do that we'd have to get, say, 10%, which would be 6.8 ohms. 4% would be 3.4, so it'd be 68 minus 3.4, 68 minus 3.4, and 68 plus 3.4, and they are the ranges down there, 64.6 and 71.4 ohms. The last part of the homework was the trial quiz for week 3. And very quickly, we've got a circuit here which said if the switch is closed, so we close that switch, straight away we've got the 660 ohm resistor comes out of circuit. 25 volts then distributed through 330 ohm, 275 ohm, 275 ohm, 1K. Add those together, divide them into the 25 volts, and you'll get 13.3 milliamps. Question 2. Study the printed wiring board resistance between pin 3 and pin 4. Here's pin 3. Let's get a different color. Pin 3, we follow it through, and it's great if you can do this with a colored pen. Through the resistor, back down here, follow it along, and back out here. So there's only one resistor involved, and that is 560 ohms. The resistance between pin 8 and 9, this was a very quick question, look at that. 0 ohms. It's a link on the board, it's a short circuit. Question 4. power dissipated by the 82 ohm resistor, you needed to work out RT, then you needed to work out the current, and then you could use I squared times R, or even V times I, or V squared on R again, to work out the power in that one resistor, and it worked out to 35.3 milliwatts. The next question, question 5, we covered this in topic 6, sources of EMF, and A is obviously out of the question. C sounds good, but more turns of the key word is there, same wire. If it's the same wire, it's got the same gauge, therefore you're going to have more resistance because of more turns, and you're not going to get more current out of it. You'll certainly get more voltage. That's why I'm putting a tick next to B, but C will be incorrect. And of course, less turns of wire and the same magnetic field gives more current, no. Question 6. I went out of my way to draw this with copper and iron, and put a bit of a flame underneath it. That is a thermocouple. Question 7. We've got two batteries which are aiding each other in this circuit. Negative is connected to positive. So we had to add the two resistors together, 267 ohms, 8 volts. There's the maths to give close enough to 30 milliamps, 29.9 milliamps. Last question, and it's interesting here. I'll talk about this answer in just a moment, but the first answer, switch is open, R1 voltage will be. So if the switch is open, we can just ignore the switch. We've simply got two batteries. They are aiding each other at the moment. That is positive to negative. That's 50 volts. 50 volts, we've got all of those resistors in circuit because the switch is open. So we had to add that to that to that to that to that. Then we work out the total current, and then we can multiply that current by the resistance, and we can get the voltage, V equals I times R. And that was in fact 25.48 volts. The next question, this one was misinterpreted by the colleague. I think maybe he needed another cup of coffee at the time, but switch closed. When that switch is closed, we've put a short circuit across the 82 ohm resistor. And what he said is 26.6 milliamps. Well, what he's misinterpreted that as is that, maybe I'll just rub that out for a second, and we'll put a different link in there. And that link will put a bit of a current meter in there, like that, current meter. All right. Now, this is how I'm looking at this. Calculate the current flowing calculate the current flowing in the 82 ohm resistor. So if we've got a short circuit across that, he's looked at the current flowing in the short circuit, which is the same as putting a current meter here, or the same as putting a current meter here. So what he's given me is the total circuit current without the 82 ohm resistor in there. So it's an easy enough mistake to make, but if we really examine that question correctly, the switch is closed, the current in the 82 ohm resistor, well, I need to just rub this out and draw a current meter here. Current. How much current will there be in the 82 ohm resistor with a piece of wire going around the whole thing like that? The answer is zip, zero. There'll be zero current going through the 82 ohm resistor because all of the current will go through the wire which is across the resistor. So look, all I can do there, put an exclamation mark. He's not the only one that did that. And I'll just write there, careful. To be careful when you answer a question like that. Always think exactly what the question is asking you to do. So that was the week 3 homework. This is Greg Moore for TAFE New South Wales. I hope those answers helped, and please don't forget to review this, and I hope that you all did well with answering those questions. See you next time.